welcome to your 6th lecture in the Embedded System course. So in the last lecture we stopped at the registers and we said that every feature and control in the microcontroller is enabled using the different registers that are present in the microcontroller, and in order to find out what registers are concerned with a particular feature, all you have to do is open the datasheet and go ahead and check the different registers and their description, and to see where to put ones and zeros in order to enable or disable a specific feature, function, etc. And we've seen a program in Embedded C, and you see how we mask the bits and how we bit shift and how we change the values inside the different registers for the different ports in order to be able to read data from the outside or write data to the outside. The same principle applies to every other feature that could be present in a particular microcontroller or generally in an embedded system. What we're going to see in today's lecture is, instead of programming registers, we're going to use the libraries that the previous scientists or engineers created for us, and those are even more friendly from a user point of view, and we're going to talk about those talk about them in today's lecture. So you've seen the lowest level ever that we can program as human beings is the machine code. However, the machine code is a stream of bytes, so it's machine readable and not human readable. So there's a other side of the same coin that we've seen in last year's CA course. Can you name it? And again, don't forget to pause the video whenever I ask a question so you can get to reflect on the question that I'm asking and try to answer it yourself before resuming the video. So the lowest human readable layer would be the ISA, so the instruction set architecture, and in our case throughout the course I'm using the Atmega as an example. So you can have a higher layer than the ISA. That would be the assembly. Alright, so the assembly language, and the assembly language, as we've seen in MIPS for instance, is nothing but the ISA itself, but it also includes a bunch of pseudo instructions that are made for humans to use, and then they're divided into different ISA instructions that are actually readable and understandable by the machine. Above that layer, we can have what we've seen in last week's lecture is the embedded C, for instance. And here we're using the C language in order to program the registers using their names. So all we have to do is put values, particular values, 8 bits or hexadecimal values, in the names of the registers that are concerned with a particular feature. So for instance, if we want to choose the direction of a particular port in order to define it as an in port or an out port, we can use the DDR register, for instance. Alright, so the last layer is the thing that you'll be using mostly during your tutorials in combination with the embedded C, but mainly the Arduino language. You'll be using it in the tutorials and especially in your project as well. You should know that what we usually do in the industry is that we first check if something already exists or has already been developed for us, so we could get to use it or optimize it and then use it. And if it is the case, it's way easier to use something that has already been invented, so we don't get to reinvent the wheel. However, if a particular feature or particular functionality does not exist, no one worked on it before, so you can get to work on it from scratch. And this could be an added value. In our case, we're going to use the different libraries that in which are defined the different functions that we can use in order to manipulate the registers without even using the embedded C layer. Alright, so here's a first example here. And what you need to learn about the language that we're using with Arduino is that we always have two functions, at least two functions in any Arduino program. So basically the setup function and the loop function. And you can remember from last time when I talked about the embedded C, when I showed you the embedded C example, we used the while one loop, and that's a perpetual loop, an infinite loop. And for what reason do we need infinite loops, especially in the context of embedded systems? The answer is whenever we turn on an embedded system, it needs to run perpetually in order to be able to interact with the environment. So basically when we powered it on all the way until we powered it off, the embedded system will keep on executing the different function in a perpetual way, hence in a loop. Alright, so back to our example here, we have two functions. The first one is the setup and the loop. So the setup is essential in order to prep the things before executing the loop. Alright, so let's see this example. Here we're defining two constants. One of them we're calling it's an integer, and it's called the bottom pin. And here you can notice we're assigning number 2 to our bottom pin. More importantly, we can see that the second constant that we're defining, which is an int as well, we're assigning to it the number 13. This should ring a bell. So if you remember the Arduino Uno picture that I showed you a couple of lectures ago, we said that there is a particular debug LED that is present on the board, and that debug LED was physically connected to some pin. And you guessed it right, the pin to which the debug LED is connected is the pin number 13. Hence, this means that we're using the debug LEDs and defining it as our LED pin. And we're doing the same for the pin number 2, and we're going to use it in order to, as the name tells us here, as the button pin. Alright. What I'm going to do next is gonna create a variable that will be used as an indicator of the state of the button that will be connected to pin number 2. So I'm initializing this variable with the value 0. Right? So these are the prep work that I'm doing here, and then I'm gonna enter the setup to do some things concerning the direction of the pins, etc., etc. Alright, so the first thing I'm doing here is I'm calling the function that is called pin modes. So pin modes has two attributes here. It takes a pin number. In our case, we're using pin number 13 that we called let pin, and we're defining it as an output. So pin number 13, to which the physical onboard debug LED is connected physically, is now defined as a digital output. Alright? This means that when I call this function in underneath that, what's happening is we're controlling which register. So we're controlling the DDR register, and we're defining it as an output. So we're putting a 1 in the relative pin, and in the bit that is relative to pin number 13. Alright, now I'm doing the same thing but in the opposite direction for the bottom pin now. So for the pin number 2 here, I'm defining it as an input. Fair enough. So in my setup, I've chosen my output to be number 13, and I've chosen my input to be number 2. Perfect. You should know that my setup is executed only once. So when I flash my program, my setup is executed only once. When I reset my program, when I reset my microcontroller, what would happen to my program? So remember, the program is loaded in a flash memory and it's not volatile. So it means that when I reset my microcontroller, whatever I uploaded before will always be there. So my program will always be there. So when I reset my microcontroller, I'm gonna go ahead and enter the setup again in order to do the proper prep for the loop function. Fair enough? Perfect. Now the loop. As I said, it's a perpetual loop. It means that as long as my microcontroller is powered on, it will keep on executing over and over again. So we're gonna start from the very first instruction here. So what am I doing? You can see that I'm reading digitally. So remember, in order to read digitally, I need to do some stuff about the registers. Which registers? So definitely the DDR register and some other registers. And those are the port and the pin. Alright? So this is completely transparent to me now because it's happening in the library. All I care about is I'm calling the function that reads digitally whatever is connected to the bottom pin, which is pin number 2. Alright, so I'm gonna check the state now. If it has a logical 1, so if it's turned on, all I'm gonna do is, if it's pushed, all I'm gonna do is turn on the LED. So I'm gonna do a digital write to the pin called LED pin here, so pin number 13, and I'm gonna put the value 1. If it's not pushed, if the button is unpushed, what would happen? I'm gonna turn off, put a 0, drive my LED pin 0, so I'm gonna drive it low, and I'm gonna turn off the LED, the debug LED that is connected to pin number 13. Fair enough? Perfect. And I'm gonna do it over and over again. So I'm gonna constantly, perpetually be testing if my button is pushed or unpushed in order to know whether to turn on or off the LED pin, the LED. Alright. Now, as promised, throughout the course, I'm gonna be using some real-life case studies, and today's case study is about a spacecraft that is called the Clementine. So you can imagine yourself as part of a task force, let's say employed by NASA, and you're studying something wrong that happened with the spacecraft. So first off, the picture that you're seeing right here is the picture of a meteor that is called Geographus, and this one is actually close to Earth. So let's see what happened. So in 1994, the Clementine spacecraft was launched, and it spent 2 months mapping the moon, and then the NASA people decided to make it head towards the asteroid, not a meteor, sorry about that, the asteroid Geographus. Alright, so they needed to do some studies about this particular asteroid, and they wanted to use the Clementine spacecraft that was already mapping the moon. Alright, now as embedded system engineers, we're gonna go ahead and check the embedded system that was used in that particular spacecraft. So the Clementine spacecraft used the dual processor Honeywell 1750 system. So this embedded system is a dual processor one, right? And it had some dedicated tasks, and those tasks were telemetry. This means that sending data to Earth, and then it has some other functions. Note that the 1750, so the embedded system here, could control the thrusters. So this is what makes the spacecraft move around, right? However, it did so only in emergency situations. This means that it was not normally meant to control the thrusters, just in emergencies. And the thrusters operations were controlled from Earth by ground control. Alright? So the Clementine spacecraft moved around using commands sent from Earth. So what happened? Let's see. On one day, and on May 7th to be exact, 1994, so the embedded system experienced some error, and it is a floating point exception related error. So a floating point exception, and we've seen that in the OS ports, that an exception is something that is unexpected, and it happens during the execution of a particular process. So it can result in an interrupt, for instance, in order to handle the exception. So what happened is, this is not very shocking, because there were some 3,000 exceptions prior to that particular day detected and handled properly. However, you can feel, or you can sense, that something special about this particular day. Otherwise, I wouldn't talking about it in this case study. So the problem here is, on May 7, the downlink data, so the data that was supposed to be sent to Earth, started varying in a wild way, so sending gibberish and then making no sense at all, and then suddenly no more data was sent, so the data froze. Of course, the task force, so the operators, the human operators, they spent some time trying to back the system to life again. So they tried sending software resets. So I can make an analogy of the software reset with, if sometimes you're working on your smartphone and you're using a particular app, and then this app freezes for some reason, all you have to do is go ahead and try to kill it, right? However, sometimes you are able to do that, or if you're working on your PC and you open the task management system, and you can kill a particular program that is running. However, they were unable to do so because they all were ignored. All the software resets they attempted to do were ignored. Finally, what solved the situation is a distant hardware reset. So basically, you can do the analogy with your smartphone and consider that you've actually pushed the button enough time. I mean, you kept your finger on the power button enough time in order to reset your whole phone. And you can remember my talks from the previous lectures when I told you that when you hardware reset everything, you go back to some state called a stable state. And a stable state is where you have the initial values upon reset, and we've seen them in the registers. So we have a field that is called initial value, and you can see the pre-programmed value whenever you have a reset. Alright, so the Clementine was back online, so people were able to communicate again with it and get the data. However, there was a problem. So the problem here is that we lost all the fuel. Someone might ask, how come? So you can remember from two slides ago, I said that the embedded system is meant just to deal with some functions, and the main function was the telemetry. However, it was also programmed in emergencies to deal with the thrusters. So apparently, the system considered that what went on is an emergency, and it dealt with the thrusters, hence emptying the fuel. So this is an evidence that was studied later on and analyzed later on. It suggests that the embedded system locked up, so basically it went bananas, right? This is due to the software crash, and then the embedded system, so the processor, kept on turning on the thrusters and dumping fuel, and the spacecraft kept on spinning around and round and round. Alright, and you can see that we have no more fuel, hence we cannot go to the to Geographis and do the missions, so it was abandoned. Alright, so later on engineers tried to analyze in hindsight how this problem could have been avoided. So my question to you is, and this is what I asked in the face-to-face lecture, is try to analyze the situation and propose a system where we can avoid a scenario like a catastrophic scenario like this one. One of the interesting answers that I had this morning, and that was the one that I needed to hear, is we noticed that the only solution that solved the problem is a hardware reset. But the problem is we had to manhandle it, so manually do it from distance, of course, because you cannot just send anybody to space. I mean, in space, in order to physically reset the embedded system. This is easy if you're doing it in your lab, but it gets a little bit complicated when you want to do it in space. So someone suggested that we have to kind of automate the fact that we're gonna do a hardware reset, and the automation could be based on some time, some kind of deadline. So we can assume that if something goes wrong, after a little while, with it we can keep track using a timer, for instance. Well, if the software freezes, let's say after 5 seconds, we're gonna go ahead and reset the whole system to a stable state. And that was the right answer. Alright, so let me give you the possibility or explain the feature that enables this particular solution. And by the way, this feature existed in the embedded system of the Clementine. However, there was a collective decision not to use this particular solution, and then they regretted it. And this is usually what happens in projects. Sometimes come up with an idea and then it's ignored. This is why you need to really argue and know how to sell your ideas, especially in the industry. Alright, so I'm putting a funny meme here so you can link this particular meme to the name watchdog. So each and every time you're gonna think about the watchdog, you're gonna remember the meme, and hence the different things that I'll be explaining in that particular slide. Alright, so what's the idea here? So the idea is we're gonna use something called the watchdog, and it follows the paradigm, the kick the dog timer. So I'm not endorsing kicking dogs in real life, it's just the paradigm that we're engineering it. Alright, the idea is if the software freezes for some reason or misbehaves, some dog will bark and reset the whole system. How can we make sure that the dog will reset the system randomly? Well, we're gonna implement this process each and every time the software is running smoothly and without any problem. Somewhere in the software, I'm gonna kick the dog. Say that I'm fine, I'm okay, don't bark. You can hence imagine that if the software runs wild or freezes for some reason, the kicking the dog would not happen. Hence, the dog will bark and reset the whole system. Right? So as long as your software is working correctly, you're gonna keep on kicking the dog. And once your software is not working anymore, the dog will notice that the software is not kicking it anymore. Hence, it's going to bark and reset the whole system. Perfect. Because it's a timer, so it will say that I'm gonna wait for within 2 seconds. If no one kicks me, I'm gonna bark. So it needs some kind of clock. Another name for a clock that we learned in this particular course is an oscillator. And I'm telling you that we're gonna use for the dog a separate oscillator. Why is that important? Why do you think that engineers decided to implement it this way? Definitely in order to have some safety, because if we're using a separate oscillator, so it's kind of redundancy, and we're making sure that the oscillator that is related to the kicking the dog that resets the whole system is has a separate oscillator that is not the common one, because if something goes wrong with the common one, I'm still having my own clock, so oscillator, in order to be able to correctly time whether the software is kicking me or not at all. The watchdog actually operates in 3 different modes. One of them is definitely resetting the whole system, but there are different modes as well, and you can get inspired from the OS course from last year. Alright, so resetting the whole system or an interrupt. So if something goes wrong with the software, I can just call the interrupt handler, so a special kernel function that will take care of a particular error or something that would have happened. If it doesn't solve the problem, or I don't want to even go there, I can go straight forward to a system reset. Or the third operating mode is go ahead, interrupt, and then do a system reset. Why do you think that this option is possible? Alright, so imagine that your software did not freeze, but it had some kind of error. So I need to handle some stuff, finish up some functionality that I'm doing, maybe save some data, maybe write down what happened, and then reset the whole system. So I will be able to call the interrupt handler to do something, and then go ahead, once it's done, I can reset the whole system to make sure that I'm starting at a stable state. Alright, because it's a timer, so we have the feature of choosing the different timeout periods. Alright, and again, all you have to do is to refer the datasheet to the datasheet of the embedded system, microcontroller, or any other embedded system that you're might be working with. and to see what are the different options. So they can go from from 16 milliseconds to 8 seconds in the case of the Atmega microcontroller that I'm using. But you should always refer to the microcontrollers datasheet in order to be able to know exactly what are the different possibilities. And last but not least, and this is an extremely important feature, we have an optional hardware fuse. This means that we can, in hardware, uh, uh, using a hardware connection via a fuse, we can get our watchdog to be always on, right? And this is for fail-safe mode. This means that if we don't want to program our do not want to program our watchdog using software, we can actually use purely hardware in order to make sure that my watchdog is always on. Alright, so here you can see the logical design, and this should bring back memories from the DSD course. So what can you see here? So we can see the oscillator, the separate clock that we talked about, and then we have some kind of prescaler. So what would that be for? So the prescaler is actually uses the oscillator in order to divide the frequency into so many other smaller frequencies in order to be able to choose the timeout period. Correct. So here we can see the different options that we can have as timeout periods, and then they enter a mux. And remember, a mux from the DSD, it has some select signals here, and those are the select signals. So how many select bits do I need here? So we can count the number of the inputs, and we can see that we have 10 inputs, so at least 4 bits are needed. 2 to the power of 4 is 16, so it's fair enough. 2 to the power of 3 is 8. No, so yes, exactly 4 bits are needed. Alright, so here those bits will enable us to choose the particular timeout period using the frequency divider from the separate clock that we talked about. And then, knowing your DSD by now, you can notice that we have a bunch of inputs, and then we have some gates, and then we have the features that we talked about, either reset the whole microcontroller or raise an interrupt, or we can have both. So this is the logic behind it. Question: where do I find information about those things here? Answer: in the data sheet. And we've seen when we talked about the the ports in general, so the inputs and outputs, that we need to set up a bunch of registers in order to be able to use them. It's exactly the same thing. So if you want to use the watchdog timer feature, we're going to go ahead and find the register that is related to the watchdog register or registers. We need to check the data sheet, right? In order to be able to know how to set it up and how to run it with the needed options. Alright, so my register that is concerned with the watchdog, it's WTT, yeah, so it's watchdog timer something, and the R stands for register. And you can notice, exactly as most registers, if not all, for the Atmega that I'm using for my for my course, as an example, it has 8 bits. Alright, and you can notice that those inputs are somewhere here, so we can see the WDE, we can see the WIF, and the WDIE, which is here, and then we can see those here. Alright, right, so the register is called watchdog timer control register, and then we're gonna see how to use the watchdog for a system reset, how to use it for a interrupt, or for both. In order to do that, all you have to do is refer to the datasheet. And in the datasheet, we can see the different options that we have. So we have the WDE field, the bit here. If it's set to 0 and the WDIE field is also set to 0, this means that I have no action on timeout. I'm not using the watchdog. Alright, so forget about this field for a second here. Alright, if I set the WIE, so you can notice that the I is for interrupt. Alright, this means, and this one is 0, this means that I'm using my watchdog exclusively in interrupt mode. Then I can only use the system reset mode by enabling the WDE field here and putting a 0 in the interrupt. So this should be a system reset. And of course, if I want both, all I have to do is put 1, 1 in both fields. Right? Finally, what I needed to notice that this last line here, we have unknown values and we still have a system reset mode. What would that be? Well, actually, all you have to do is read it. So here you can notice that we have the WDT on, always on, fuse. So remember, this is the hardware fuse that I talked to you about in the previous slide. So when it's 0, it means that it's actually on, and when it's 1, it means that it's unprogrammed, so it's off. So we don't have a fuse. So you can notice when we have a hardware fuse, we don't really care about what we are setting up using the software, remember, because we're going to write 1s and 0s in the different fields. So it doesn't really matter. It's unknown what I have here because this one is forcing the system reset. Fair enough? The last thing I need you to notice here is this particular field. Whenever you read enough, usually enough is for a flag. So this seems like it's a flag for some reason. Alright, last thing that I need you to notice is the initial value. So yeah, this is classical, we've seen those before. Whoop, something's fishy here, and then this is classical. So why would the bit that would actually make my system reset be unknown, on reset according to the initial value? Why wouldn't it be 0 or 1? So let's think about it for a second. Imagine that my system is reset on a watchdog timer timeout, meaning that for some reason my watchdog reset the system. If I had a 0 here as an initial value, this means that I'm not enabling the system reset mode. So each time I reset my whole system, by default, I don't have any watchdog timer. That would be crazy, because if my system reset is caused by a watchdog timer, so the very next time I'm having a timeout, right, I won't be having any system reset. So it doesn't make any sense. The answer to that, this should be, and this is the case, this is related to a particular field in another register. So basically, if the system is reset upon a watchdog timer, so I know that it's the watchdog timer that caused the reset, so I need to write 1 here to make sure that for the next timeout, if it ever happens, I'm gonna reset my whole system again. So this is unknown because it's dictated by another field in another register. Speaking of which, I have a special register called MCU status register. So this is the status register for the microcontroller, and in it I'm going to see different fields. So forget about the reserved one for now, and let's talk about those one. You can see that I have a flag. So remember, the F stands usually for flag. I have a flag that indicates whether my system reset is caused by a watchdog timeout, and if it's the case, I'll be reading a 1 here. Reading a 1 here, and you guessed it, will cause the WD, the field that is the WDE fields in the a watchdog register to be set to 1 to make sure that the watchdog is still on. Fair enough? So this is the flag telling me that the timeout caused the watchdog timeout caused the system reset. What about those? Can you guess what those are? So flags for, let's start with that one. So PO is power on reset flag. This means that we have a power on reset, so we just powered on our microcontroller. An external reset flag, this means that someone pushed the button and caused a reset of the microcontroller. And the last one here, if you remember it from the different features that I exposed when I talked about the Atmega, this is the brownout reset flag. Brownout, remember, as opposed to blackout. So this is, if a reset occurs because of the brownout, we will find a 1 here. Alright. I don't want to program the registers using embedded C. I'm gonna try and see if someone created libraries for me so I can just call functions, and it is the case. So here we're gonna see an example. First of all, let me check the hardware of the system that I'm trying to implement. So you can notice here that I'm attaching a push button to this particular pin here on this board, and this is an Arduino DC1000. Alright, so my push button is connected to pin number 2, and then you can see that it's connected to the, what is that? To the ground. Perfect. Via a resistor. What do we call this resistor here? It's a pull down resistor, correct? And then you can notice that the red wire here is also connected to the button, and it connects it to the 5 volts of the board. So what happens is when I push the button here, I'll be creating, you know, a connection between the VCC and number 2, so I'll have a logical 1 here. When I leave it, I will be having a logical 0. Make sense? Perfect. And here I'm having also, remember the debug LED that is on board here, and it's also connected to pin number 13. So let's see the software now. So this is the hardware of my embedded system. I want to see the software. Alright, so in order to be able to use the watchdog, the library, I need to have the header, and it belongs to the AVR family, and especially the header, the watchdog timer header. Alright, I'm defining first LED 13 because I want to use the onboard LED here that is physically connected to pin number 13. So yeah, so LED is the pin number 13, and the button is the one that I'm connecting the push button to, and it's pin number 2. Fair enough? Alright, so remember 2 functions in each program. The first one is the setup. So this is what I'm doing. I'm choosing the mode. Remember, if I want it to be an output or an input. So this function is what sets the DDR register for the different ports. So yeah, so pin number 13, the LED here, I'm defining it as an output, right? And pin number 2, which is the push button, I'm defining it as an input. Makes sense? So when I push the button, I'm taking it as an input. I'm going to control the LED normally. The LED will be controlled by whatever output I'll be having. Here, it's a delay. For the time being, just see it as something to waste some time. So for us human beings to be able to see if something's going on, because it's a delay of 2000 milliseconds, so 2 seconds, so we can observe it ourselves and notice if something's going on. All right, because if it's too small, if I don't put a delay, everything will happen so fast, it will be flickering so fast I won't see anything at all. And the last thing that I'm doing in my setup, I decided to turn on my LED. So I'm writing digitally to my LED high. I'm driving it high, so I'm gonna turn it on. So making my LED output, my button as an input, wait for 2 seconds, and then turn it on. And then, last but not least, I'm using the function WTT enable, so watchdog timer enable, right? So I'm turning on my watchdog software, so no hardware fuse here, nothing at all, software. And you can guess it from here, I'm choosing the timeout period for 1 second. Fair enough? Alright, so this is the setup. Now I'm gonna go to the loop. This is a perpetual loop, and it will keep on, as long as my microcontroller is on, it will keep on executing it. So what I'm doing in the loop is, if reading high on my button, so if the button is pushed, all I have to do is kick the dog. Alright, so if I'm kicking the dog, this means that the watchdog will not time out. If I don't push the button, so the dog will notice that it hasn't been kicked for some time, after 1 second, and it will reset the whole system. Resetting the whole system means that I will go all the way back to here to execute everything that I'm executing. Make sense? Alright, so let's see a video that I've recorded in my office, if I'm able to turn it on. Alright, so here you can notice the push button, and you can notice the board with the LEDs. So LED number 13 is, resetting. So let me do it one more time. So you can notice here the LED is turning on and then off, and then on and then off. This means what? This means that because no one is pushing the button, the watchdog is noticing that it's not being kicked, hence it's resetting the whole system. So we can see LED number 13 turning off and waiting for it to be digitally turned on later on in the setup function. So what happens if I push the button now? So here you can notice that I want to push the button, and I pushed it, and hence the LED is not turning off again, no more. So if the LED is not turning off, this means that the button is pushed, right? And I'm resetting the watchdog. I'm kicking the dog, hence the system is not being reset. Alright, that was the last thing that we've seen in today's face-to-face lecture. Should you have any questions about it, don't hesitate next time you see me to ask me about it.